work we present today is about using a surrogate model to quantify the thermoacoustic instability risk given the input parameter uncertainties. Our work aims to address a very common issue in practice, that is, when we do not have enough computational budget to train a perfect surrogate model, then how can we still use it to obtain a reliable risk calculation? This work was done by me and other coworkers in TU Munich. When we have uncertainties in flame model parameters or acoustic boundary values, the prediction of the mode under investigation may jump between stable and unstable. It is a common practice to use Monte Carlo simulation to propagate the uncertainties. Simply put, we draw a large number of samples from the input distribution, and we call some acoustic solver to calculate their corresponding growth rate values. Based on the ensemble of these outputs, we can simply count how many of them are above zero, and this portion is defined as the instability risk, PF. To avoid calling the thermoacoustic solver over and over again, we can train a surrogate model instead to accelerate this uncertainty propagation process. First, we draw some representative samples from the input. We call some acoustic solver to calculate their corresponding responses. Based on this training dataset, we can fit a surrogate model. Later on, we can apply Monte Carlo procedure directly to the surrogate model and instantly obtain the output distribution and its associated instability risk value. This idea sounds attractive, but we have to be really careful here, because in reality, it is very common that we may not be able to afford this many training samples. And when that happens, our surrogate model will be inaccurate, and as a consequence, the output distribution and the instability risk value will also vary. In summary, due to the limited training data, our surrogate model will be uncertain, which prevents us getting a reliable risk calculation. Now the question is, how can we minimize the impact of surrogate model uncertainty and still manage to get a reliable risk calculation? That's exactly what we are trying to address in the covered work. We do that in two steps. To reach our final goal of reducing the variation of risk calculations, well, first, we will need to be able to quantify this variation. We will start the presentation by introducing the case study we are investigating. Then we'll go through those two steps. I will illustrate the main ideas and apply those ideas to the case study. Finally, I will summarize the main conclusions. So for the case study, we adopted a network model as the thermoacoustic solver. This network model represents a turbulent premixed swirl combustor test rig. For the flame dynamics, we employed an impulse response model proposed by Komarek and co-workers. This model assumes that the shape of the flame impulse response can be approximated by adding three Gaussian distributions, with one positive Gaussian to account for the flame response to axial velocity fluctuation, and one positive and one negative combined together to describe the response to the swirl number fluctuation. The parameterization of this flame model is shown here. So tau1 and sigma 1 here are the mean and the standard deviation of the response to the axial velocity fluctuations. Tau s1 and tau s2 represent the characteristic time lags for the response to the swirl number fluctuations. For those parameters, we consider them uncertain. 10% around the mean are the uncertain ranges. Tau c here denote the time lag for an inertial wave to travel from the swirler to the flame base. In the current study, we assume this parameter is fixed at its nominal value. Finally, we focus on the quarter wave mode of the combustor. Due to the uncertainty in flame model parameters, the growth rate value may also go above zero. In addition, we use Gaussian process as the surrogate model. So Gaussian process is a Bayesian method, and it's especially powerful in modeling the spatial data. It assumes that the function we are trying to approximate is a generalization of Gaussian process, which is characterized by a mean function that describes the general trend, and a covariance function that describes the spatial correlation. Usually, the mean takes the form of a polynomial function, and the covariance function, also known as the kernel, usually looks like this. By using the training data, we can estimate the values of those polynomial coefficients, sigma squared and theta, that best fit the data. Then we arrive at the posterior. We simply use the mean function as our surrogate model. The posterior here also gives us the prediction uncertainty, which is the key to quantify the risk variation. Okay, so let's see how exactly we can do that. When using GP as the surrogate model, the prediction of the sample will not be just one deterministic value. Instead, we will get a Gaussian distribution around it due to the uncertainty embedded in the GP model. This is also true when we do Monte Carlo simulations. Luckily, we can automatically obtain the mean and the covariance of those outputs through GP. Detailed formulas can be found in our paper. Later on, we can generate realizations from this multivariate normal distribution, and each one of those output realizations will yield a slightly different risk values. Then, based on the ensemble of these risk values, we are now able to quantify the variation of the risk calculation. This approach is straightforward, but here's the catch. Recall that we need this amount of samples for performing Monte Carlo simulations. In that situation, our covariance matrix will be really huge. And as a result, generating realizations from this covariance matrix will be extremely low in efficiency. So how can we solve this problem? Well, although the predictions are uncertain, not all of them will affect risk calculation. For this prediction, for example, its mean is pretty far away from the stability margin, and its distribution is quite tight. Therefore, it is highly likely that this prediction will remain positive. For this prediction, on the other hand, its distribution does not exclude zero, meaning that it may be positive or negative, therefore leading to a variation in the risk calculation. So this observation informs us we can actually divide those predictions into two groups based on this U index, where the mu represents the mean of the prediction and the sigma represent the standard deviation of the prediction. So we use the threshold of 3, and we only consider samples within 3 sigma distance, and we only generate their realizations. For samples that are outside of 3 sigma distance, we simply just use their nominal value and ignore their uncertainties. By doing this, the size of the covariance matrix will be significantly reduced, therefore improving the efficiency. We apply this methodology to our case study. So first, to train the GP model, we use this number of training samples. Those samples, they are generated by Lardin hypercube sampling method. The benefit is that the generated samples can evenly fill the parameter space. Afterwards, we use this GP model to calculate the instability risk of the quarter wave mode. If we do not consider the uncertainty in GP model, we will get a deterministic value, 7.8% for the current case. Well, this is not very helpful since we have no clue how accurate this result is. Now we consider GP uncertainty. Instead of getting a single value for the risk, we can now quantify the uncertainty in risk calculations as shown here. This is a much more informative result since we have a better idea of how good this estimation is. Those two results are all obtained via applying Monte Carlo simulation to the trained GP model. Recall that the GP model is only an approximation to the original network solver. So what's the reference risk value when we apply Monte Carlo simulation directly to the network solver? So here is the reference results. We can see that by taking into account the GP model uncertainty, even though the mean prediction is not exactly correct, its distribution still covers the truth. Therefore, this PDF is much more informative than this point estimation since it gives us a sense of how accurate our estimation is. Also, it would be interesting to see how the PDF of the risk calculation varies when the number of training samples is gradually increased. To investigate that, we do 3 case studies with different training samples. All of them are generated by Lardin hypercube method. On the right, we have the results. Clearly, we can see that with more training samples, the mean value of PF moves closer to the reference PF value. Besides, the PDF becomes more concentrated. Both evidence indicates that the accuracy and robustness of the GP models improves with more training samples. This conclusion is somehow expected, but what's more surprising is we need to throw 400 training samples to get a decent instability risk estimation. This is obviously too much of computational effort in practice. So, is it possible to reproduce this PDF with a much lower sample number? In fact, we have already revealed the secret earlier. The key is there's no need to make GP prediction very accurate for output like this, since they are very unlikely to affect risk calculation. Instead, we should focus on those samples that are very close to the stability margin. As a result, in the beginning, when we decide where to put our training samples, this sampling scheme that even if fill the parameter space is just a waste of a resource. Instead, we should allocate more samples in the vicinity of the stability margin. This way, we are able to achieve a more accurate and less uncertain risk calculation. In order to do that, we can adopt an active learning scheme. So first, we have some initial training samples and we train a GP model based on those samples. Meanwhile, we maintain a pool of candidate locations and we will pick our next sample from one of those locations. To do that, we use the newly trained GP model to make predictions at those locations. Then we simply pick the location with the minimum U value. A location with a small U value means that this location is very close to the stability margin. Then we calculate the corresponding true growth rate value by using the network model. Then we add it to the training dataset, and then we can update the GP model. And we repeat this process many times. So here we compare the results of active learning scheme and the naive space filling scheme. Both are using the same number of training samples. We can clearly see that the accuracy is much higher and the uncertainty is much lower now. This indicates that active learning scheme did fulfill the promise. Okay, to summarize our current work, in pursuit of obtaining a reliable calculation of thermoacoustic instability risk by using an imperfect GP surrogate model, firstly, we demonstrate how to quantify the variation in risk calculations by taking into account the GP model uncertainty. Later on, we demonstrate how to minimize the impact of uncertain GP model by successfully allocating training samples in the vicinity of stability margin, therefore significantly increase the accuracy and reduce the uncertainty in risk calculation given the same computational budget. Before we finish, I would like to briefly discuss how this work connects with other of our studies in a broader context. So for the past 2 years, we have been working on mitigating some acoustic instability risk by implementing the principles of robust design. Our very first study following this line of work is the paper Efficient Robust Design for some acoustic instability analysis, a Gaussian process approach. In that study, we investigated how to mitigate risk under different scenarios. We formulated the risk mitigation problem as optimization problems, where at each optimization iteration, we use a GP model to perform an uncertainty quantification analysis to determine the corresponding risk value. In that study, we focus on developing this overall workflow and simply assume that the employed GP model is perfect without any uncertainty. Clearly, this assumption is not always valid in practice. So what would happen if we only have an imperfect GP model? This is what we have addressed in the current study, namely to quantify and subsequently reduce the variation of risk calculations. The competence we develop here can be directly integrated into the robust design workflow we proposed in the previous paper. That would enable us to perform reliable risk mitigation in realistic settings. Of course, our current study is not free from limitations. Here, we are calculating the instability risk for only one mode. What if we have multiple modes that are potentially unstable? Can we extend the current methodology to efficiently tackle system-level instability risk calculation? This motivates our next study to develop strategies to calculate thermoacoustic system instability risk with uncertain GP models. Compared with our current study, this new study features several important improvements. First, we adopt a more intelligent sampling scheme that can track the system stability boundary. Secondly, we employed gradient-enhanced GP to improve the training efficiency and accuracy. Here, the gradients are calculated by an adjoint solver. In addition, we have other improvements, including using more advanced acoustic solvers, more uncertain parameters, and larger variational ranges. We will submit this work to combustion flame soon. That's all about this presentation. Thank you very much for your attention.